Hello everyone and welcome. So we're going to be working through an example of a convolution integral, how to do this computation, in the hopes of gaining a little bit of facility with it and also understanding a little bit of what it's doing, like what mechanically is going on with this weirdly defined thing. So the example that we're going to be doing this on is the following set of boxcar functions. F of t is going to be equal to 1 on the interval from 0 to 1, and g of t is going to be equal to 2 on the interval from 2 to 4. And we're going to convolve these two things and see what happens. So just as a quick reminder, the definition of the convolution is f star g. It's going to be a function of t, and it's equal to the integral from 0 to t of f of t minus lambda, g of lambda, d lambda. And so thinking about this geometrically, let's try to think about this geometrically a little bit. So basically, we have these two functions defined on these intervals. So the first one being essentially from here to here, and the second one being here to here. Okay, so if we look at the definition, this says we're going to be taking f, and the minus lambda reverses it around the y-axis, and the t translates it. So we are going to be looking at f of, and so this here is f of minus lambda, and then we're going to be moving that, basically sliding it to the right, and then integrating it, multiplying it by g and integrating it. So this little box is going to be sliding to the right, and then we're going to be counting the area under the product of the things. So as it slides, eventually it's going to reach here, and we're going to be multiplying these things and counting some area. And then it will be fully underneath. It's going to keep on sliding as t increases. This is going to move under, and then it's going to keep on moving and eventually move out on the other side. So we're going to try and figure out the area under the product, so 1 times 2, as it slides around. So that's what we're up to. So let's see if we can do that. So again, this is our function. We're going to be doing the convolution integral. So I'll write it down one more time for good measure. T minus lambda, g of lambda, d lambda. Okay, so thinking about where these things are defined. So when is the product going to be equal to something other than 0? So g of lambda is non-zero when lambda is between 2 and 4, right, from the definition. Right, that's what we get from right here. 0 everywhere else. Meanwhile, f of t minus lambda is non-zero when t minus lambda is between 1 and 0. That means that, well, let's solve for lambda here. We get minus t less than or equal to minus lambda less than 1 minus t. And then multiplying by the negative sign, t minus 1 less than lambda less than or equal to t. So the product is only going to be non-zero when both of these conditions hold. So we need both lambda between 2 and 4, and also lambda between t minus 1 and t. So this is an interval. The second one is an interval that's going to be changing as t changes. And so let's think about when that's going to happen. So if t is between 0 and 1, when t is less than 2, there is no overlap. So f of t minus lambda is times g of lambda is equal to 0 for all lambda. So the integral will be 0. So f star g of t is equal to 0 for 0 less than or equal to t less than 2. All right, now things start to change. As t increases, this right-hand edge of the interval for f is going to sneak into the region with in which lambda is also, or in which g of t is also non-zero. So what does that lead us to? Then we have when f is between 2 and 3, we have something like this, t minus 1 to t, and 2 to 4 are our intervals. So the intersection will be from 2 up to t. All right, this region here is where both of them are non-zero, so the product is non-zero. So in that case, we get that the integral from 0 to t of f of t minus lambda times g of lambda d lambda is equal to, well, the only lambda values that are going to matter are between 0 and t. Between 2 and t. So it's 2 to t of f of t minus lambda in that region will be equal to 1, and g will be equal to 2, and times d lambda. So we get, well, we have to take the antiderivative. We get 2 lambda between 2 and t. So we get 2t minus 4 is the value of the function there. So f star g of t is equal to 2t minus 4 between 2 and 3. Okay, next region. Sorry, this is when t is between 2 and 3. When t is between 3 and 4, well, then we have our interval from 0 to 2, or from 2 to 4, and t is between 3 and 4, so t is over here, and t minus 1 is also entirely contained in this region. So now the integral from 0 to t, the only non-zero part of that will be from t minus 1 to t, and again it's t2 d lambda that we will be integrating. So we get 2 lambda between t minus 1 and t. If we do that out, we get 2t minus 2t minus 2, which is equal to 2. So f star g of t is equal to 2 on this second region from 3 to 4. We have a couple more to do. So now let t get a little bit bigger. So when t is between 4 and 5, now there's our interval from 2 to 4. T is out here between 4 and 5, which means the tail end of it reaches back into here. So now we're looking at the interval from t minus 1 up to 4 on the right-hand side. That's the region where both of them are non-zero, so that the product is 2. Otherwise, the integral is 0. So f star g of t is equal to the integral from 0 to t, f of t minus lambda, g of lambda, d lambda. That's equal to the integral from t minus 1 to 4 of 2 d lambda. So 2 lambda from 4 to t minus 1. We get 8 minus 2t plus 2, so 10 minus 2t. That's our third region. And then finally, if t is greater than 5, then, well, we have from 2 to 4. T is greater than 5, so t minus 1 is greater than 4. So no intersection, and we get f star g of t is equal to 0 out there. All right, so let's put that all together. F star g of t is equal to, and it has several different values, 5 different values. 0, 2t minus 4, 2, 10 minus 2t, and 0. This one from 0, 2. This one from 2 to 3. From 3 to 4. From 4 to 5. And for t greater than or equal to 5. What does this look like? Well, it's quite interesting the way that it works out. We have 1, 2, 3, 4, 5. And heights of 1 and 2. So for the first 2 units, it's equal to 0. Then 2t minus 4 is exactly the line that comes through here. This at slope 2 for 1 unit. It's going to go like that. And then it's constantly equal to 2 for 1 unit. And then 10 minus 2t exactly comes back to here. And then we continue. So this is f star g of t. Those two box functions came together to this. So in the last video, I mentioned how even if you have discontinuous functions, the convolution will be continuous. So that's something. And we see that that happens here exactly as it's supposed to. So again, this is from looking at that graph that I drew. This function sliding across, as it slides across, the first little bit of it starts to be underneath here, and as it moves more, that's where you see the area under the curve going up. And then the area under the curve as it's in the middle here is constant, it doesn't change. And then the half of the lower boxcar function starts to peak out, so the intersection region where things actually count gets smaller, and that's when we see the function starting to come down. That's where we get this guy. So hopefully this calculation is a little bit useful. It's a weird thing to think about, especially all these piecewise definitions. You really have to stop and try to reason it out. There's no great systematic way to go about it. Just really have to think